All right, next section is double integrals over general regions. So we're going to talk about when the base isn't just a rectangle, it's really kind of any shape. All right, so we'll have your domain, your inputs, xy pairs, okay, such that x is between a couple values, so that'll look familiar. But y is between some functions, okay? g1 of x and g2 of x. Okay, and we could also have that as y is between the values and x is between some functions. Oops, and that would be functions of y. There we go. Okay, so the way that we set these up is we integrate first with those functions. And again, this is one of those things where once I do an example, it'll make a lot more sense. Okay. Okay, in this case, those functions are y values. So we would be our dy first, and the a and b are x values, then we would do dx. Okay, if it was the other way around, we would do this. Okay. And so sometimes either one would work for the region that we're given, and so we'll see some of those. Sometimes one of them it has to be the correct order. Okay, so I'm getting a little bit ahead. Let's look at rest of the time here. So there's going to be a bunch of examples doing that. Okay, so the first one, we have our integral of x cubed in the region. X goes from 1 to e, and y goes between 0 and the natural log function. Okay, so if we just look at that, x is 1 to e, and then y is between 0 and the natural log function, which looks like this. Okay, so there's your boundaries. Again, x values between 1 and e, y values between y equals 0 and y equals the natural log of x. Okay, so we're looking at a d right there. Y equals the natural log of x, y equals 0, x equals 1, x equals e. Okay, so that's the region that we want. All right, and now you got to think about above that region, we have that z function. Z is whatever x is cubed. Okay, I'm going to try to draw this a little bit. Okay, so it would be kind of a cubic function in the xz plane, right? Kind of like a, oh boy, and it would only depend on x. This would kind of curve around too. Kinda. I think so. This is almost like a wall over here, and then it would like slope down, okay, and have a height of 1 here. It's kind of a weird shape. All right. Anyways, so then when we do our integral, we're going to want your, let's see here, 1 to e on the outside, 0 to the natural log of x on the inside, x cubed. Okay, and again, the 0 and the natural log of x, those are y values. Okay, and then 1 and e, those are x values. So remember, you work your way from the inside out. So first we're going to integrate x cubed with respect to y. So we'll have x cubed y evaluated from 0 to the natural log of x. Okay, so we're going to have, and remember, it might be helpful to write y equals and y equals. Okay, so we're going to have x cubed times the natural log of x. And then when y is 0, we're just going to have 0. Okay, there we go. Oh, we get to do some integration by parts here then. Okay, because remember, there is no integral rule for natural log. Okay, so that is, when you do integration by parts, that is your first choice for u. And then du would be 1 over x dx. dv would be x cubed dx. v would be x to the 4th over 4 then. Okay, so we'd have the integral of u dv is the integral of, did I do that right? u dv, yeah, the integral, I'm thinking about u dv is an integral of v du. What am I, oh, I'm sorry, uv. I'm going to write it out before I start. Integral of u dv is uv minus integral of v du. There you go. Okay, so remember your integration by parts. So we're going to have u times v, so x to the 4th times the natural log of x over 4. Here's your uv, minus the integral of v du. So we're going to get rid of, it'll be an x cubed over 4 dx. And that will all be evaluated from x equals 1 to x equals e. Okay, so pop it down here, x to the 4th natural log of x over 4 minus, we're going to have x to the 4th over 16, all evaluated from 1 to e. So we'll have e to the 4th natural log of e over 4 minus e to the 4th over 16 minus 1 natural log of 1 over 4 minus 1 over 16. Natural log of e is 1. Natural log of 1 is 0. So we've got e to the 4th over 4 minus e to the 4th over 16. So that's 3e to the 4th over 16 plus 1 over 16. Okay, so we've got 3e to the 4th plus 1 over 16. Okay. Now I'm going to show you a couple other things here with this one. First of all, if we had tried to do it the other way. Okay, so we've got, take our derivative, our integral that we had set up here, bring it down here, if it lets me. There we go. Okay, so we set it up like this. What would happen if you tried it the other way? Okay, let's say we did 0 to the natural log of x, 1 to e, dx dy. Okay, at first you're okay. You have x to the 4th over 4, you evaluate from 1 to e. We'll have e to the 4th over 4 minus 1 over 4. Okay, and then we will have Well, those are constants, right? So then we would have e to the fourth minus 1 over 4y, evaluated from 0 to the natural log of x. There's where your problem is, okay? Where you would plug that natural log of x in for y, and we didn't get an answer. Our answer still has x in it, okay? And x is a variable, and that just doesn't make any sense. So you have to make sure that you always have the functions on the inside and then the constants on the outside, okay? However, we do have another option with this, okay? And it goes back to drawing our region that we started with, where we had 1 to e and then 0 to natural log. Okay, so this point would be e natural log of e. This point is 1 natural log of 1. This point is e 0. Okay, in other words, this is e1 and this is 1, 0. Okay, and this is your function. Y is the natural log of x. Okay, and then if you remember, we did x between 1 and e, and then y between 0 and the natural log of x. Okay, well, we can flip that, okay, because we can rearrange it and solve our function for x instead of y. So if y is the natural log of x, e to the y equals x. Okay, so just rearranging that equation, solve it for x instead of y, okay, then what I can do is y is between 0, let me fix that, okay, y is between 0 and 1, and x is between this function, which is e to the y, and e. Okay, so any of your y values would be between 0 and 1. Any of your x values are between this function and this function. Just like that. Okay, so I could do the same thing and do my integral 0 to 1, integral e to the y to e, x cubed, dx first, and then dy. Okay, so then x to the fourth over 4, evaluated from x equals e to the y to x equals e. E to the fourth over 4 minus e to the 4y over 4. Okay. And now I can integrate that. E to the fourth over 4 is just a constant. Okay. And then e to the 4y over 4. So we would have, think about your u sub there. If I do e to the 4y, the derivative of that would be 4e to the 4y. So I'd have to divide by 16. Evaluated from y equals 0 to y equals 1. So I would have e to the 4 over 4 minus e to the 4 over 16 minus 0 minus e to the 0, so 1 over 16. And that's the exact same answer we had before, right? Because this would be 3e to the 4th over 16. So 3e to the 4th plus 1 over 16. Okay, so you can switch out the bounds to have them in terms of the other variable if that's easier. Okay, sometimes it will be easier, sometimes it will be impossible. So you have to choose correctly there. But that's kind of the gist of it. We're going to do some examples here. So again, this is one of those videos where you should stop and try the example first and then see how you're doing, because that really is kind of all you need to get going on these. Okay. But definitely is going to help you to do some more examples. So let's try some more in this video. Okay, we've got, and these are all from the evens in your textbook too. This one is number 14. Okay, so now this is one where they don't explicitly lay out the functions they want you to use. Okay, you need to draw in that region and kind of figure out what you want to do with it. Okay, so we would have the function y equals x. We would have y equals 4. And we would have x equals 0. So there's your region. Okay, so now we have options here. Okay, we could do, let's see, if this is y equals x, this point here is at 4, 4. This point would be at 0, 4. And this point would be at 0, 0. Okay, so one option is x is between 0 and 4. Okay, x is between 0 and 4. And then y would be up here between x and 4. Okay, so x is between the functions x equals 0 and x equals 4. Y is between the functions y equals x and y equals 4. That gets us our region. Okay, so that would work. So if we're going to do it that way, we do the integral from 0 to 4, integral from x to 4, y squared e to the xy. That x and 4 are y values, so it would be dy dx. Okay, so that's one way to do it. The other way to do it is, it's blue here. We could say, well, y is between 0 and 4. So y is between 0 and 4. And x here, x is between 0, x equals 0, and y, x equals y. That also gets us the same boundaries. Okay, so our other option is to do the integral from 0 to 4, integral 0 to y squared, e to the x, e to the xy, dx dy. Okay, so take a look at that and decide which one you want to do. Okay, we take a look at this. I want to take the integral with respect to y. I've got two guys going on there. Let's see here. Would this work by parts? Let's see, integrating that with respect to y. You have to have it over x. Okay, that looks like it might get kind of messy, right? Looks like something I don't really want to do. I'm not even sure I have it set up right, to be honest. Let me think about it a little bit. U be the y squared, du be 2y dy. I mean, I guess we could then do uv minus the integral of v du. Oh man, yeah, I don't really want to do that at all, right? This is making me sad. I don't want to do that. Okay. So I'm going to look over here. My other guy, maybe this will be better. Can I integrate this with respect to x easily? Yeah, I can do that. Okay, because I would have, let's see, e to the x y. If I take the derivative of that, that would put a y out front. Hold on, my light just went out in my room. Okay. There we go. So that would look like that, right? The integral of that guy would be that, because then if I take the derivative of this, it would be y e to the xy times y. So that's good. Okay. Evaluated from x equals 0 to x equals y. So that would be then the integral from 0 to 4 of y e to the y squared minus, and I put in 0 there, it'll be e to the 0, which is 1, so y. Okay. dy. All right, and I'm going to split that up into 2. Because one of them is clearly easier than the other one. Okay, but this one's not too bad. You can think about a u sub there. And I don't know about you, but when I do my u subs, I like to swap out my limits too. Right now they're in terms of y, so I square them to get u. And I would have e to the u du, and I would need a 1/2 out front there then. Okay, so let me just kind of spot check here, make sure I did it right. E to the u would be e to the y squared. Du would be 2y dy and the 1/2. There we go. Okay, minus the integral from 0 to 4 of y dy. We're going to have 1/2 e to the u from 0 to 16 minus y squared over 2 from 0 to 4. Okay, so 1/2 e to the 16 minus e to the 0, which is 1, minus 16 over 2, which would be 8, minus 0. Okay, so I've got 1/2 e, let's see, I like to make it one expression. Okay, so I'm going to do e to the 16 minus 1 minus 8. So I'm going to change that to 16 over 2. So I've got e to the 16 minus 17 over 2. Oof, there you go. Okay, not a super easy integral to do, but definitely better than the other option there. Okay, and just be really careful. It's so hard when you have to consider one of these to be a constant. Integrating's difficult enough sometimes with your u subs and your integration by parts. All right, let's do another one though. Okay, let's see here. I already did that one. Maybe a couple more here. And at the end, we'll go over some properties that you might come across. Okay. Here's a good example. This is number 44 in your book. You have the integral from 0 to the square root of pi, and then the integral from y to square root of pi of cosine x squared dx dy. All right, so we're supposed to integrate that with respect to x, and it's impossible. Okay, we kind of have talked before. There's always derivative rules. Derivatives always work. Integrals, sometimes they don't work. This is an example of one. We cannot integrate cosine of x squared, okay? So what we do is we think about that boundary, okay? So we have a boundary that is set up so that x is between y and square root of pi, and y is between 0 and square root of pi. Okay, so what we're going to do is we don't get to choose how we're going to set up these bounds. We have to switch them in order for this to work. Okay, so if we sketch this out, x is between, let's do y first. So y equals 0. Maybe I'll use a different color for that too. Okay, so we're between y equals 0 and y equals the square root of pi. Okay, and then we have x equals y, and we have x equals square root of pi. Well, this would be at square root of pi, square root pi. Okay, so bounded by those, we're right here for your region. Okay, so we're hoping then we can switch it, which we can. Okay, if we want to switch it around so that x is between 0 and square root of pi, okay, there's your x's, then y is between 0 and the line x equals y, or y equals x. Okay, so we've changed our bounds, all right, so that now y is the one that has the function with it. So that now I can do the integral from 0 to square root of pi, integral from 0 to x, cosine x squared dy dx. Okay, and we're going to hope that that's easier, and guess what, it is. Okay, so we're going to have the integral from 0 to square root of pi. This cosine x squared is just a constant, so cosine x squared times y, evaluated from y equals 0 to y equals x. So we got the integral from 0 to square root of pi of x cosine of x squared. Okay, and if I plug in the 0, I get 0. There you go. And so we got a u sub there, right? U is x squared. Du is 2x dx. So we'd have the integral from 0 to pi of cosine u du. And so we would need a 1/2. Okay, and an integral of cosine of sine from 0 to pi. Sine of pi is 0. Sine of 0 is 0. So we get 0. Okay. There we go. A little anticlimactic there, but we get 0. Okay, but you can see, like we were talking about before, that order, the purple one that we started with, it just doesn't work. So we have to switch it out, okay, and hope for a better setup there, which we got. I'm going to go over some properties, and then we're going to do one more example, okay? So there's a bunch of properties on page 706. A lot of them just kind of make sense. In fact, I think we covered some of them in the previous video. Double integral of a sum of two functions. We can separate them. That makes sense, right? Okay. Next one, the constant. I'm not really sure why they repeat these again. I guess it doesn't hurt.
Moving north,
Okay. Oops, I missed my C there. Those constants can come out. Okay. Next one too, I think we saw before. I'm not going to talk about these too much because I feel like we did in the last video, and they also just kind of make a lot of sense. Okay. The next one's kind of, excuse me, kind of a new one. If that region that you are integrating over can be written as the union of two separate regions, where D1 and D2 don't overlap, except they can on the boundaries, okay, then okay. And this is really similar to what we learned in Calc 1. So we had the integral from a to b of f of x dx. If c is between a and b, okay, then that'd be the integral from a to c of f of x plus the integral from c to b. Okay, so it's similar. Where they don't share that point of overlap, they share like a boundary of overlap, which would be fine, okay? And that's useful if D is something like it's kind of a blob. Okay. Thinking about how we would integrate that. Okay. Trying to set up some boundaries would be very difficult, but what you could do is something like this. Okay, we could split it up into 3 different regions. D2 is what we call a type 1 region, which means that we can integrate it, between x values, or f of x's, I guess I should say. We could, that top could be like f of x, the bottom could be like g of x. You would run into issues if you try to do the same thing on the other ones. These are called type 2, where we would be better off integrating those. So this. I guess I didn't do a great job there on the hedges. I guess I just wanted.
North and Rebecca Cregan, please report to the office.
Maybe if I do that more. Okay, but just between functions of y, it would make much more sense to integrate that this way than try to do it the other way. Okay, and same with this one. It would make much more sense to integrate it that way. And this one, it would make more sense to integrate it that way. When you're thinking about like your top function and your bottom function, we did these in Calc 1. Okay, so you can divide it up into different regions like that if you want. Okay, there's another one that will kind of actually come in handy later. Integral over a region of your constant function, dA, gives you the area of D. Okay, which is kind of interesting if you think about it. If you think about your region D, I'm trying to draw this in like 3 dimensions. If I wanted to find that area of it, I could think about the constant function z equals 1. That's supposed to be the same shape. Okay, so like a height of 1. So this is in the xy plane. This is z equals 1. Okay, so in this case, the volume would be the area of D times 1. So the area of D is that volume, right, divided by 1. Okay, so if you integrate your constant function over that region, you get your area there. which is kind of weird, but it works. Okay. Then, and that, again, that comes in handy later. Okay. And then your last one here, if m less than or equal to fxy less than or equal to big M. Okay. For all xy in D, then we know that that integral, oops, okay, so if we think about this a little bit here, try to draw. Okay, so we have that some region in the xy plane that we're going to integrate over. Okay, and then we've got this function okay, and we want to integrate it over that region. Okay, we can show that there might be some value z that function is always between that purple, curved surface is always between the plane z equals little m and z equals big M, then this should make sense, right? This volume and this volume would bound this volume. Okay, it's like an example. It's kind of a weird example. It's, we have an example where it says estimate integral over d of the square root of x cubed plus y cubed dA, where d is from 0 to 1 in the x's, 0 to 1 in the y's. Okay, well, this function over that domain is between 0 and square root of 2, right? 0 would be the smallest it could be. Square root of 2 would be the biggest it could be. Okay, so then in the area of D is 1, right? A 1 by 1 square. Okay, so this integral dA, okay, is somewhere between square root of 2 and 0. Okay, and that's the best estimate you can really get, right? But there you go. Okay, so again, have some fun with these. Make sure that you're really understanding some of those, the one that we did, where was it? Up here where we changed the bounds, because that's going to come up again. That's going to come up a lot. We really have to understand how we're getting those bounds and how those work. Okay, so really make sure you understand what we're drawing when we draw those graphs like that, and how we're switching between stuff like this and stuff like this. Okay, all right, see you guys later.